Hey everybody, welcome to NASA Launchpad. I'm your host, Scott Bednar. Do you know who this guy is? Well, you should. That's Sir Isaac Newton. You may have heard of the story of an apple falling on his head, leading to a greater understanding of gravity. The story may not be entirely true though. The apple may not have really hit him on the head, but one thing that is true is that Newton's laws of motion have a huge impact on everything we do. Not familiar with Newton's laws of motion? Well, let's run through them very quickly in simple terms. And hey, you can try this at home. Center an index card over the top of a glass and put a coin in the middle of the card, like so. Then carefully flick the card to one side. Cool, the coin dropped right down into the glass. Now put the coin on a flat surface and wait. Still waiting? Notice that the coin just sits there. It is not moving anywhere by itself. You have just witnessed firsthand Newton's first law. Objects tend to keep on doing whatever they're doing, staying at rest or staying in motion, unless something else exerts a force on them. Of course, that's net force. Think of it this way. If two guys are trying to move a couch, and one of them pushes in one direction, and one pushes in the other direction, the two forces are balanced and cancel each other out. The couch doesn't move, and it is the same as no force at all. But if a third guy comes up and joins one side, you would have a net force, something left over when you figure out all the forces acting on something. You can't just add up the numbers to see if there is a net force. Direction is important too. We'll come back to that. Now on to Law 2. A net force acting on an object causes the object to accelerate. We'd better go back and figure out what acceleration is first. Acceleration is any change in an object's speed or direction. The acceleration depends on the amount of force applied and the mass of the object being moved. When you add lots of force to an object, it accelerates more than if you add less force to an object. Once again, makes sense, doesn't it? Finally, Law 3. When an object exerts a force on another object, the second object exerts an equal and opposite force back. Need more info? Let's head to the International Space Station, where it's actually easier to observe Newton's laws in action. Here's astronaut Dan Tani with some demonstrations.
Let's pretend like I'm on the ground in your classroom. And if I were to take one of these candy-coated chocolates and let go of it, what would happen? Oh, it would go crashing onto the ground, wouldn't it? And then when I ate it, it would have to be a dirty chocolate that fell on the ground. The reason that happens to you in your classroom or on the ground is there's a force exerted on the chocolate, and that force is provided by gravity, okay? And that force is always straight down. So if you were to drop the candy-coated chocolate, it would fall to the ground because it has a force imposed on it. But here in the space station and in low Earth orbit, we are under microgravity, which is essentially no gravity, no apparent gravity. So if I let go of the candy, it doesn't fall. It stays at rest because there's no external force on it. Okay? Actually, there's a little force because we have fans going, and so the force is provided by the airflow. But basically, there's no force on it until an external force is imposed on it. Like that.
Newton's first law only makes sense if you think about all of the forces affecting an object. If you throw a ball here on Earth, pretty quickly it stops moving, right? So what are the forces that are at work? Gravity pulls the ball towards Earth. Friction is a resisting force caused when objects rub against each other. These forces are acting against the first force, you throwing the ball. So a battle of forces is taking place. Eventually, the forces balance each other out and equilibrium is established. So the ball returns to rest, or stops moving altogether. All right, back to Dan for the second law.
So F equals ma, and that's a pretty simple equation, but it really means a whole lot to people who study how things move. And let's do a little demonstration of F equals ma. I'm down here on the floor of the space station, or we call it the deck, because we have some bungees set up. Bungees hold our stuff down. But a bungee is a good way to impose a particular amount of force on things. Let's put this candy under a little bit of force and see what happens. The force that the bungee exerted equals the mass, which is small, times the acceleration that it experienced. Okay? So big acceleration, little mass for the same amount of force. Okay, so force equals ma. So let's do that, put that force on the old hammer. Okay, you see that? A lot less acceleration. So the force is the same, the force from the bungee was the same, but the mass was really small for the chocolate. It experienced a bigger acceleration, so it's got a faster speed. But the bigger mass, the same amount of force, results resulted in a slower acceleration.
So, if you've got the same force acting on two objects, the mass and acceleration of the objects are inversely proportional. It's algebra. Bigger M, smaller a. Bigger A, smaller m. And now for the grand finale, Newton's third law. And here's Dan again with a big bag of water to show how it works.
Okay, so what happened there? I pushed away the water, and I lifted my feet so I was floating, and it went away with the speed, and I went away with the speed because when I pushed, that action had an equal and opposite reaction on me. So the force that we pushed the water off, I used the same force to push myself back, okay? But I went slower because I have more mass than the water. And this is how rockets work. What rockets do is they throw out their propellant. Propellant is really heavy. All that mass gets used to propel the shuttle into orbit. And what it does is the rocket engine create combustion, and it spits out the mass of that propellant out the back of those engines. And that mass pushes, and that force pushes the shuttle into space. And that's how rockets work.
So, a rocket carries fuels which explode when mixed together. The gases from the controlled explosions are forced out of the rear of the rocket at a really high speed. The large mass of gases push back against the smaller mass of the rocket, and the rocket accelerates forward. Newton's third law in action. From card tricks to the International Space Station, Newton's laws help us understand and explain principles of motion. You want to find out more? Well, visit NASA's Teaching from Space website at the address on your screen. That's all for this episode. Until next time, I'm Scott. Catch you next time on NASA's Launchpad.